Okay, good morning. So let us continue our lesson. So if you remember, the last thing we talked about was the notion of a locus in geometry. And there are some famous loci that I want to talk about them today, try to understand this. So a very famous one that it is ubiquitous everywhere is the circle, yes? So the circle is the locus of all points which are equidistant from a fixed point, yes? So that is called a circle. And then if you remember, last time we talked about another very famous one. I give you two fixed points, yes, call them A and B. And then I ask you about the locus of points that are equidistant from these two fixed points, yes? And then we realize what that locus is the perpendicular bisector of the line segment AB if we are confined to, if we are restricted to work on the plane. Okay, so and then I told you that to prove that a proposed geometrical shape is a locus, we have to do it in two ways. Yes, we have to pick a representative point on the locus and show that that point enjoys the property of that locus, but that is not enough. We also have to show that if a point enjoys that property, definitely it lies on that locus that we have described. So whenever we want to solve a locus problem, automatically, if you want to prove it rigorously, we have to do it in two ways. Yes, that's the thing that we need to know. There is also another, so remember these things. Yes, so this is a very famous one. And if I don't want to restrict myself to the plane and ask you the same question. Okay, I have 2 points A and B in a space, and then I want to talk about the locus of points which are equidistant from these 2 points but lie in the space. I want to relax that condition that I have to be on the plane. And then, do you have any idea? Just intuitive thinking is enough for me. I don't want to prove them rigorously. So here I have 2 points, but I'm allowed to be in the room. Yes? So what that would be intuitively? Yes?
Like a wall between them?
Yeah, exactly. A plane. A plane that actually is perpendicular to this line segment again. Yes? And it goes from the middle of that line segment. So if we want to relax this condition that we have to be on the plane, then it becomes a plane which is passing through the middle and is perpendicular to AB again. Yes, for example, if you consider this tip and that tip, my hand is the loci, is the locus of those points. Yes, is that intuitively clear? Okay. Now another very, very famous one, probably, is this one that I want to mention. But before that, I want to ask you: if I give you a point, if I give you 2 points, and I give you a precise ruler, and I ask you what is the distance from A to B, this is easy. You can measure, you can just connect these 2 points and measure the length of that line segment. That would be the distance from point A to point B. But now let me change this setup. Instead of 2 points, I give you a point and I give you a line. Okay? So this is your point and this is your line. I want you to know this definition. If I give you again the ruler, probably it's not enough to measure the distance from the point A to the line L. This needs a definition because the line L includes infinitely many points. But when I talk about the distance from a point to a line, I mean the shortest distance. Yes, so that is the definition. Okay. So in that case, I have to be able to draw a line perpendicular passing through A and perpendicular to this one. Then this can be shown, this is the shortest distance. And then you measure this length. This length is called the distance from the point A to the line L. Yes, so that is the definition of the distance from a point to a line. Now, the question is that if I give you two parallel lines, so L1 and L2 are parallel, I ask you, what is the locus of points in the plane that are equidistant from these two lines? Intuitively, just think intuitively. I am looking for the locus of points on the whiteboard that are equidistant from these two lines, L1 and L2, assuming that L1 and L2 are parallel. Yeah, intuitively, what's that? Yes?
Infinitely.
Okay, but what is the load? So you cannot say that there are infinitely many. Yes,
But
there are infinitely.
But there are one of the same size.
No. What is look? I want you to understand this question. When I ask you the locus, you need to give me a shape or something. Describe the properties of those points. Yes, Dennis?
A line in between.
Yeah. You should say a line. It's not possible to say infinitely many or something. It's important. It's a line which is parallel to these two and is exactly passing from the middle. Yes? So in principle, I draw a line, any line works, that is perpendicular to both of them simultaneously, and this is possible because these two lines are parallel. And then I draw the perpendicular bisector of these two. Yes? So the perpendicular bisector of these two will be here. So this line, which I call it L, is the locus of points that are equidistant from these two lines, L1 and L2. Is that understandable? Yes? Okay. But the natural question is that, what happens if L1 and L2 are not parallel? Okay, so if L1 and L2 are not parallel, this is intuitively very clear, but probably when L1 and L2 are not parallel, that's not that trivial. It's very, very simple, but probably it's not that easy as this one that you can guess. Okay, let us, for the time being, focus on rays instead of lines. Rays are actually half lines. They have a starting point, so let me make an angle here. And then I will also talk about what happens if they are actually lines, not rays. Yes? So, what do you think in this case? My question is again the same. Here, let me again call it ray L1. So let me call it, yeah, it's good. L1 and L2. And I'm asking you the same question. What is the locus of points that are equidistant from these two lines, rays L1 and L2? These are really important questions, so I want you to understand them. For example, let me just try to understand what is going on. For example, just intuitively, do you think this point works? I will come to you, okay? Do you think this point works? Why not? Because the distance from this point to this line, I have to draw a perpendicular line. This would be distance 1. And the distance from this point to this line, I have to draw a perpendicular line. Yes, this is D2. And clearly D1 and D2 are not the same size. So it means that this point is clearly not one of those points. Okay, so you need to think in this way, so that I need to start moving this point somewhere, so that this distance and that distance become exactly the same. And then intuitively it might help you. Whenever you have a good guess about the locus, you claim that this is the locus, and then you have to prove that this is indeed the locus. So if you want to find the locus, you have to have an intuition. You need to have an educated guess about the locus. And then if someone says, how do you know that this is the real locus? Then you have to prove it in two ways. Yes? Choose one representative on the claimed locus and show that it enjoys the property. And then just take a point which enjoys the property and show that this is on your claimed locus. And then you are done. Now, do you have intuition about that?
It's a guess.
Yes?
But a line passing through the angle bisector
So why do you say passing through? That's the angle bisector.
Yeah, well, yeah.
The angle bisector.
Yeah, the angle.
Yeah, that's very important. So remember these famous loci. Okay, I told you loci is the plural form of locus. So yeah, please remember this. And this is it was very clear. So probably you will not ever forget this. But this one needs a little bit of better understanding. So yes, now we have a claim. We have an educated guess probably by some kind of intuition. And now this is not enough. We have to show it. Yes. So what we can do, we can just draw this angle bisector. Angle bisector is this one. I try to do this angle bisector. So making this angle alpha, for example, and this angle alpha. We are claiming that this red ray, by the way, is the locus. Okay, now you help me. How should I prove this rigorously? Yeah, this is a standard. So I pick a representative, not random, a representative point on the locus and try to show that this enjoys the property of being equidistant from the lines. Yes? So what I do, I take a point here, a representative, let me call it A. I want to show that the distance from A to L1, which is this line, is equal to the distance from this point to this line. Yes, I want to show that these two blue lines, let me call them AH1, AH2. So, and let me call this delta. So, yeah, usually let me just use it delta, this letter delta. So I know that A belongs to delta. I want to show that AH1 is equal to AH2. Here the premise is this one, the conclusion is this one. Okay, so why they are equal? Yes?
Because they're congruent.
Why?
Angle side angle.
Angle, side, angle. Which angles? Can you tell me?
Alpha. And
Alpha is equal to alpha. Then
they share one side.
they share one side. Then
And then you can just, it's 90 degrees then.
yes.
100.
So if this is alpha, this is alpha. This is 90. This is 90. So this is beta. If I call this one beta, I can also call this one beta. Yes. Because the sum should be. Okay, and then I have two angles and the side between them. So these two triangles are congruent, and when they are congruent, it automatically tells me that AH1 is equal to AH2. Yes? So this is one thing, but it is not finished now. So what I have to do, I have to reverse the order. So I now assume that AH1 is equal to AH2. I need to ask myself, is this true that A belongs to delta? Okay? So I have to clean this now because I don't have the delta here. Delta is the angle bisector. So here I know what I know is this one. Yeah, they are. You might say that this is trivial, but it is. I want you to understand this point from mathematical point of view, that this is not trivial. This is the opposite. This is called the converse, by the way. If P then Q, this is called the premise or hypothesis, and this is called conclusion. If I write it Q, remember this terminology. This is not called the inverse or reverse. It's called the converse. This implication is the converse of the previous implication. And there is no relation whatsoever between these two in general. It might happen that this is true, this is false. It might happen that this is false, this is true. Might be both of them true, might be both of them false. Yes, this can happen. Here we have to show that both of them are true. That's the point. Okay, now I know here AH1 is equal to AH2. I want to show that A belongs to delta. So how should I do that? So you see there is no track of delta yet. I just know that AH1 is equal to AH2. I want to show that A belongs to delta. What delta is the angle bisector. How should I show that A belongs to the angle bisector?
Do we still have alpha?
No, there's no alpha. This is the shape that I have right now.
Okay.
It becomes exactly the same shape as before, but I want you to understand what I know. I have a point, which I know the distance from that point to L1 and the distance from that point to L2 are equal. I want to show that A belongs to delta. If someone asks what delta is, I would answer that delta is the angle bisector. Why it belongs to the angle bisector? what is the first step to do? You need to write it in words. I need to add something to the picture. So what's that? Okay. You are a little bit still slow here. Might be you are confused. Is that confusing or not? Okay, so I want to show that A belongs to delta. The delta is not in the picture. I would say that I connect the vertex to A. Yes? And I prove that this green line is delta. Do you understand what is the logic? So I do not have delta at all here in this part. I am telling you that A is some point and this vertex is a point. I can connect them. It's always possible. But then it is not guaranteed that this is delta. I want to show that yes, this is really delta. Yes? How should I show that? I need to show that this angle and that angle are the same. You see, the logic is, so it is very delicate. I want you to understand, because these are very, very simple things for you to do, but the logic and understanding these things are actually very important. So now I need to prove that these two question marks are of the same size. But why they are the same size? Because this time I know that this blue line is equal to that blue line. Yes? And I know that this hypotenuse is common between these two triangles. Okay, so it means that the third side should also be equal, based on Pythagoras theorem. And then these two triangles are congruent because of side, side, side. And if they are congruent, these two angles are the same. Is that understandable? So this finishes the proof. If I know that A belongs to the angle bisector, it is equidistant from these two lines. And if I know that a point is equidistant from these two lines, then it lies on the angle bisector. This is one of the very famous and very simple loci, yes? Okay, so now what happens if they are not rays, but they are actually lines? This is very easy to understand now. So instead of having rays, I have two intersecting lines, and I'm asking you the same question again, but I think this is easy for you to understand now. So I have two intersecting lines. I had the parallel lines. It was intuitively very clear. You immediately answered that. Now by this one you can also answer that. Now my question is that, what is the locus of points equidistant from these two lines on the plane? Yes, Kevin?
There are two loci.
Yeah, yes.
One passing through horizontally and one passing through vertically.
Yes, but you said there are two loci. Be careful, there is only one locus. This thing is the locus. Okay. This terminology is important. You see, the whole picture that you described for me is one locus. It's not two loci. Yes, is that understandable? So, and then I hope that this is clear. So the locus is this red part of the red part of the whiteboard. It's not possible to find something else. So every point that I choose here is equidistant from these two. If I choose here, it's still equidistant from these two. And if I find a point which is equidistant from these two lines, it lies somewhere on these dotted lines, where we don't know. Might be there or might be here. So is that understandable? So that's important to remember. Okay, for example, and then I want to give you a very important tool. It's called the method of two loci. Extremely important. If I want to locate a point in geometry, this is a very important tool. For example, I give you a triangle. And I ask you this question. You see, these are very simple questions, but I think it's really important. I'm asking you, is there any point on the whiteboard which is equidistant from the points B and C and simultaneously equidistant from the sides AB and AC? So you see, if possible, I want to locate some point on the whiteboard which is equidistant from these two points and simultaneously equidistant from these two sides, which you, of course, you can continue. And by the way, I should probably a little bit careful. If I ask you what is the distance from this point to this line segment, what is the distance from this point to this line segment, you need to continue this and then draw this perpendicular line. So this would be the distance. So I should have mentioned this here. If I have a line, I do not have any problems. It goes to infinity. But if I have a line segment and I ask you what is the distance between this point and this line segment, you have to continue it in appropriate direction and then draw this perpendicular line. So now my question is again, can you tell me how should I find that if there is such a point? Yes?
Is it that you draw the locus for the points and then the locus for the sides and then see where the intersect?
Exactly. So that's the method of two loci. So you know that because you are looking for a point which is equidistant, you see it might be a little bit hard. If you don't have any strategy to solve the problem, it might be hard to find the point. But now, if you see that, okay, on the one hand, the point that I am interested in should be equidistant from these two. Forget about the rest. But we already know the locus for this. It means that we already know all the points with that property. Yes? What are those points? I find the middle point and then draw the perpendicular bisector. So if I ask you what is this blue line, you would say this is all possible points that are equidistant from these two. Yes? But there is no guarantee. So if I take a random point, if I find the distance from this point to this line, this would be this one. And if I want to find the distance from this to this, I have to continue this. Yes, and then draw that one. I don't know, might be, I don't know. If they are equal, this is one of those points. If this is not equal, that is not one of those points. But I cannot just start trying and detect every point to see if it works or not. And as actually you told me, that is probably the best way to understand that. So what I do, now I forget about this, I concentrate on the points which are equidistant from these two sides. So probably this is the angle bisector, yes? This angle bisector. Okay, and then I'm a little bit unfortunate. Okay, so they intersect here. So this point lies on the red line, so it is equidistant from these two sides. It also lies on this blue line, so it is equidistant from these two. So the point of intersection is a point with both properties simultaneously. And that is exactly what I want to find. Yes? Is that clear? For example, if I ask you, if I give you a line, and a line L, and I give you a point, let me call it A. If I ask you to find a point on the line which is, I don't know, 5 meters from A, how do you find that point practically? I want to find a point on the line which is 5 meters, for example, from A. Just describe the methodology. Yeah? What is the answer? How should I find the point? So this is also the method of two loci. One locus is the line itself. Yes? Because I want to find a point on this line. So one of the loci is this. But forget about this. I also want to have the point 5 meters to A. What is the loci? What is the locus of these points? What is that? The circle centered at A with radius 5 meters. So what I do, I draw a circle around this with radius 5 meters. Assume that this is 5 meters. Okay, let me change the center. If this is 5 meters. And then I look for the intersections. Yes? So this point, if I find the intersection between these two, this point lies on the line, so that's good. It also lies under circle, so it means that the distance from this point to its center is 5 meters because the radius of the circle was 5 meters. Yes? And then what happens here, I have another point. So I found 2 points. Okay, but there is no guarantee that I always find 2 points, yes? Let us discuss about those situations. If A is very far away, when I draw that circle, there would be no intersection points. So it means that don't look for that point. You will never find that. Yes, because there are no intersections. It might be that this case, you will find 2 points, but is it possible that we find exactly 1 point? Yes, and that is exactly when this circle touches this line, but does not intersect that. It becomes tangent to that. In that case, we have 1 point. I just want you to understand, even though this problem was so simple, if you do not learn to think systematically, it becomes a little bit hard. Okay, so these things. Okay, now that we know a little bit about the notion of the locus, let us see what we can do. Do you remember we have 3 important Sevian lines in a triangle? One of them was median, median. The other one was angle bisector. The other one is altitude. Yes. So far, we have shown completely rigorously that the medians are concurrent, that they pass through exactly 1 point. If you remember, we proved that. But we want to do the same thing for other things in a triangle. We want, for example, let us start with angle bisectors. Why do you think angle bisectors should be concurrent? It's not trivial, yes? I just draw a circle. I just draw a triangle here, ABC. And of course, I draw one angle bisector. Let us consider this. I will try to make it to equal parts. So let me call this AD. This is, for example, angle A1. This is angle A2. I am assuming that they are equal. Let me just draw another one. It's clear that they will intersect. Yes, this is clear. But this is not clear that the third one will also pass exactly through this intersection point. So let me call this one angle B2, angle B1. So my assumption is that these two are the same, angle bisector. These two are the same, angle bisector. They will intersect at some point. Yes? And now, what I am claiming is that, do not look here, you draw the angle bisector of the third one. In principle, it could pass from any other point, but it does not. It passes exactly through this point. Why? It's much simpler than you might imagine. But the problem is that you do not have the proper mindset probably. Yes?
You draw the locus of, I suppose, AD, or like, you draw the angle bisector and...
No, this is already an angle bisector. This is already an angle bisector. This is already an angle bisector. They intersect at a point. My point is that why, if I draw the third angle bisector, it also passes through, in principle, who knows, it might go pass very close to it, or it might pass from here. Why it is not possible? It only passes through this point. Yes, Jonathan?
If you draw the locus of the point or the lines AD and B to the other one, then you will have one of the lines going through C where the angles are the same.
Okay, but how?
Because of the thing you...
No, you need to tell me exactly, okay? Not because of the things, you need to you need to state your statement precisely.
Because of it's the locus, then it becomes
Okay. Let me try to motivate you in this way. I want to show that the third one passes through this point. Let me call this point I. By the way, this is a standard. Okay, I is a standard here. And the reason that this is the center of inscribed circle, I will tell you why. Okay, so this point is important here. But what I'm saying is that I do not forget about drawing the angle bisector momentarily. Instead of doing that, let me just connect this point to that point. You see, I am not drawing the angle bisector. I'm changing the logic a little bit, but understandable. I'm just telling you that when I find this point, I connect it to C. My claim is that IC is the angle bisector of C. If I can prove this claim, then I am done. Agree? Is that understandable for everyone if I can show this? Okay. But how should I show that this is the case? Let me ask you something. I really want you to be able to answer these. Okay? I draw a perpendicular line from here to here. And let me call it H. Let me call it H1. Okay? And then I draw a perpendicular line from here to here. Okay? And I will call it H2. And I do the same thing here. Okay? Why all of them have the same sizes? It's very awful picture here, but all of these orange ones should be of the same size. Yeah, it's very, very easy, but you need to train your eyes because when the picture becomes complicated, you might not be able to detect the pattern immediately. Yes?
Because of angle. So the lower
No, I don't. Yes, you are right. Yes, completely right. But I don't want to start from scratch. Use what we learned. Of course, you can always go and prove everything from scratch. I don't want you to do that. So, for example, I am claiming that H1 is equal to H3. Very simple. Because we just showed that. What is this one? This is angle bisector of this. So every point on the angle bisector is equidistant from the sides. So that's it. Because of course what you wanted to show is correct, but we have already done it, yes? So we don't need to do it again. I would say that I belongs to the angle bisector BE. I belongs to BE, and BE is angle bisector, is the angle bisector. Okay, let me write AB for angle bisector. So what is the conclusion? It means that H1 is equal to H3. Do you understand this one? Yes or no? Because we just showed that if a point is an angle bisector, it is equidistant from the sides. You agree? Okay. Now, I have the same strategy. Let me change my color here. I would say that I belongs to AD. And AD is the angle bisector. Yes? What can I conclude? Okay, tell me, what is the conclusion? Which ones are equal? H2 and H3 should be equal. Yes? But now compare these two. What you can conclude from these two? That H1 and H2 are also equal. Yes or no? But if H1 is equal to H2, it means that I belongs to the angle bisector of C. Why is that? So this means that I belongs to the angle bisector of angle C. This last piece I want to understand. I want you to understand. Do you understand the last part? Why is that the case? Okay, so let me repeat it again. If I have an angle, if I give a point here and I give you this information, the distance from this point to this line and the distance from this point to this line are the same. What is your conclusion? Where this point is located? We just did it. Yes?
Belongs to the bisector.
It belongs to the bisector. And that's happening here. The distance from this to this side and the distance from this to this side, H2 and H1, we showed that they are equal. So I belongs to the angle bisector. That's it. As simple as that. But I want you to see, it seems a little bit of convoluted logic, but it is not. Is that understandable? Let me just repeat. I know this is probably when of course in Swedish system we do not have anything like this, but when I was at your age, when I was studying this for this concept was a little bit confusing for everyone. But let me just try to see. I want you to fully understand what is going on. So you see, if I draw an angle, if I myself draw the angle bisector, if I draw the angle bisector, okay, look at here, just read. I have an angle, I myself draw the angle bisector, and I choose any point on this line. If I ask you, can you, in English, can you say a property of this point? What is your sentence? Just tell one property. Of course, you can say a lot of things, but one of the properties that is in this context. What is the property of that point? Just repeat it, yes? Yes?
It's equidistant from the line.
Lines. Yes? Now let me change the logic. I do not have the angle bisector at all, but I just have a point and I give you this piece of information. I tell you that I measured the distance of this point from this line and I measured the distance from this point to this line and I saw that they are equal. What would be the conclusion? If you want to, it is on the bisector. Is that understandable? So this is very easy. So this is bisector. I know this is angle bisector. So the distance from I to this and I to this are the same. I know that B is, this one is also angle bisector. So the distance between here and there are the same. From logic, if they are equal to H3, so they have to be equal. Now I know that I have a point which is equidistant from this line and that line. So this means that this point should lie on the angle bisector. So this means that this is angle bisector. I want you to understand this logic. Of course, you can start from scratch and solving everything from scratch again. I don't want you to do that. Is that understandable? Okay. But there is a very nice property which was not that easy. If I have given you this riddle, I give you a triangle, and I ask you to draw a circle so that its center is inside the triangle, and it is simultaneously tangent to all three lines. If you want it, it's not easy. I don't know where you do want to start. If you want to start, I don't know, because you want to draw a circle, you know. If you make it tangent to this one, it is not tangent to this one. It's not that easy to adapt that, yes?
I mean, it should be centered at point I with the radius.
Exactly. So that point I has this property. Yes? So if I find that point, because these three lines are equal, so if I put the needle of the compass here and open it from one of them up to one of them, when I draw that, it automatically passes through these 3 points. And because they are perpendicular, so it becomes automatically tangent to all of them simultaneously. Yes? So and that circle, which is a very bad shape if I want to draw it here, but hopefully you agree, you accept it from me. This circle is called inscribed circle. The inscribed circle. Yes? So remember, whenever you want to draw that, and then what is the role of H1, H2, and H3? All of them are equal. That would be the radius of that circle. Yes or no? Okay. And this is a good problem to solve. If I give you the sizes of the sides, how can I find the radius of the inscribed circle? It's easier than you imagine because we did the hard work yesterday. Okay, so how can I find the radius, the size of the radius of the inscribed circle? So let me go back here. And so here, I don't know how should I draw it by hand. So yeah, let me draw the circle first. This is a little bit of trick. And then I draw tangent lines, yes? I don't know, something like this. My question is this. I give you, of course, this is not equilateral. This is just a coincidence if it looks like an equilateral triangle. My question is that I give you the length A, B, and C, the sides, and I ask you, by the way, the standard notation is little r. The radius of this in geometric text is called, is denoted by letter R. Capital R is reserved for something else. We will talk about that later. Okay? So I want to measure the radius. So the center is called I, and then I want to calculate this radius. If I give you A, B, and C, how do you calculate this? Any clues? Do you remember what we calculated yesterday? We were able to calculate medians, angle bisectors, heights, and the surface area. We were able to calculate all of them using the ABC. So let me give you a guide. So here the surface area is very important. Surface area of the triangle. It seems a little bit strange, but it will work. Let me guide you another time. So you see, by the way, what is this angle? If this is the point of tangency for the circle, we have this in Mat 2C, so that is 90 degrees, yes? So let me now connect this point to that point. Do you think it will help? Because in principle, let me call this A, B, C, then from here to here is how much is A. Can I calculate the area of this smaller triangle? What is the area? Yes?
A times R divided by 2.
Exactly. But I don't want to solve the problem. The problem is actually solved. Can you just take one more step, two more steps? So this is what this number, if I ask you what this number is, you will tell me this. If I hatch this, this is this area. Yes? Okay. What was your goal? Do you remember how much I repeat this? Your goal is to find a formula that expresses R as a function of A, B, and C. This is unfortunate a little bit because this S we don't know yet. If I knew this side, then I just divide everything by A over 2, I am done. But the point is that I don't know this, but in principle you can immediately do something. Yes?
You can do the same thing.
Exactly. We can do the same thing from other sides, yes? I can connect this one to this one as well. Yes? So this side is B. Okay, can you tell me what is the area here? What would be the area here? Can you give me the formula? S I A C. Can you tell me what can I write in front of this one? 1 over 2 BR. Everyone agrees with that. Because B is the base now. But what is the height? The height is again R. Do you agree? The height is the same thing. Yes or no? Okay, and then it becomes clear. I will calculate S of what? S of IAB. So what is the answer? It is 1 over 2 C dot R. Understandable? Okay, then what? Yes?
Yeah,
You add them. Because when you add them, what will happen if you... Giving me this one. So if I add them, what happens? I have to add these sides. But what would be these if I add them? This area plus that area plus that area becomes the area of the triangle, which we denoted by S. And then when I start adding them, what can I do? I can factor a 1 over 2r out. Yes or no? And then what is left? A plus B plus C. Yes, but what was this in geometry? 2p. And this 2 and that p cancel. So we get a nice formula. S is just PR. Okay, and then R is S over P. So this is a very simple and nice formula. That is the formula that you get for the radius of the inscribed circle. Did I achieve my goal? Yes, because do you remember we had the Heron formula yesterday? So if I give you the length of A and B and C, you can find S using that Heron's formula. And then of course P is just adding them and dividing them by 2. Understandable or not? Okay, so that is also so very, very important to know about geometry if you like geometry, of course. Okay, good. Now let us go to another problem. There is also another famous circle. This time it's called circumference circle. Okay, if I give you the same game this time, let us have this game, okay? I give you a triangle. This time, let me start from this. It's probably a little bit motivating. The problem is so simple. I ask you to draw a circle that passes through A, B, and C simultaneously. The problem as simple as that. Okay, when you are thinking, so let me just open this GeoGebra. So is the question clear? I want to, if it's possible, it might be, it's not possible, I don't know. But if that's possible, is there any systematic way that I can draw a circle that passes through these 3 points simultaneously? Okay, so here, for example, let me just get rid of these axes here. So how should I get rid of axes here? Okay, so assume that I have my triangle. So let me just draw a triangle here for you. This is my triangle. And what I want to do, I want to draw a circle that passes through these 3 points. If you don't have a systematic way, this problem is actually really, really hard. Okay, for example, let me just use this. I don't know, where do you want to... So for example, let me start from here, okay? And then, I want to force this circle passes through those, okay? I got A, but it will not ever, so if I go to B, I lose A. Is that understandable? And if I want to go to C, I lose both of them. Okay, so you might say that, okay, you can solve the problem, so let me just go back and draw another circle. I don't know what, yes. For example, where do you think? Do you think that you can do it? Yeah, can you do it? Not systematically, just randomly. Randomly is not possible. I just want to feel that this is not an easy task. Yes, it might happen that, okay, I will try to do it and it will eventually pass. I don't know. For example, let me take it a little bit closer because somehow I have a hunch where the point should be. So let me take this one and try to draw the circle. You see? Yeah, I am getting closer, but still I lost. Yes? So it means I just want to motivate you that this is not possible if you just want to do randomly things. But now can you tell me, how can I do it systematically? How should I do it systematically? This is my question now for you. Do you know how in GeoGebra I should get rid of all these things simultaneously? don't know, in classic 5 it was easy. You just press Ctrl A and then just delete everything. It's start playing game with us, you know. What is the other one? Resume recording. Yes?
So, I mean, it's systematic, but it isn't very mathematical. It's more visual.
Yeah, visual, yes.
So you can create the locus of each pair of points.
Yes.
And then see where they intersect.
Yes.
So, example, the locus of AB, and then the locus of AC, and
So
then the locus of B.
Yeah, I understand, because you're showing it with hand, I can see. But the locus of AB is not meaningful, yes? The locus of points that are equidistant from A and B, I draw that. What is that one? Is the perpendicular bisector.
Exactly.
And then you draw the other perpendicular bisector. Yes. So far, it guarantees that it passes that. Let us just do it by GeoGebra again. Okay. So let me just go here. So in GeoGebra, let me just draw another triangle here for you. By the way, GeoGebra is capable of doing these things. Okay. The problem is this. So what actually you are telling me, for example, let us consider this line segment IJ. Yes, and I want to draw the perpendicular bisector of that. Yes, so I go here, perpendicular bisector. You see, this is an option. So I choose that one. Then I just pick these points, and then I have my perpendicular bisector. So this line, this black line, is the perpendicular bisector of the line segment IJ. Yes. If I ask you what are the properties of these points lying on this black line, it is guaranteed, but what we learned, that every point on this black line has the same distance to J as its distance to I. Yes? And this is good. Why? Because if I put the needle of the compass on this, wherever I want to, on this black line, and open it so that it passes through J, it automatically passes through I. But there is no guarantee yet that that one also passes through K. Is that understandable? But at least I were able to solve the problem with I and J. For example, let me choose any point that you like here, any point, even outside this. Let me just keep it inside for the time being. I choose this point, and you see when I reach to J, it automatically passes through I as well. But there is no guarantee it passes through I. But something is clear. This point should be somewhere on this black line. Do you agree? Because if I want to be outside the black line, I will lose I and J. Yes? To pass through I and J simultaneously, I have to be somewhere here. Okay? Okay, then what? What you said is actually exactly correct. So how can I find that point? It is better than before, because before drawing this, I can have all these potential points in principle, but I narrow it down to this black line now. But still there are infinitely many possibilities. So what I have to do, I have to draw another angle bisector. So a perpendicular bisector. Which one, for example, let us choose I and K. Yes? And then what happens? They intersect at this point. What is the property of this point? This point is equidistant from I and J because it lies on this perpendicular bisector. Simultaneously, it lies on this perpendicular bisector, so the distance from here to here and from here to here is the same. So it means that all these distances are the same. So if I find the intersection point, so how should I find the intersection point? I go to points, and then I will I will actually find the intersection here, you see, intersect, and I will choose this line and that line. It gives me the intersection point. Now that I have intersection point, I go to circle, I choose circle. This is the center of my circle. It is guaranteed now. Look, I just concentrate on K. Okay, so you see, I make it bigger. I don't care about J and I. I'm just caring about making this circle to pass through K. Yes, but you see, when I reach to K, if I can. Yes, it's automatically done. Yes, so you see, it was practical. You see, it was not practical in the beginning, but now it is practical. So I started from that point. I concentrated on reaching to K, but mathematics told me don't worry about those points. It will automatically pass through those points. Yes? This N is not a standard. This is described in geometric text. Geometric text, it is called O. And this circle that passes through all these 3 points is called the circumference circle. Okay? And the radius of this circle is denoted by capital R. So the radius, if you have a geometric book, a geometry book, this is reserved for this radius. Capital R is reserved for this circumference circle. Is that understandable? Okay. So that let me just close this and don't save. I don't know how should I get rid of all of them simultaneously. And just wait a moment. So what we do. By the way, let me also test that idea here. That is good to know. So let me get rid of these axes. So let us go back to this problem. So how should I do that? Let me just draw a random triangle here. Yeah. This is my random triangle. How should I find I, the inscribed center? How should I find that? Yeah, just say something. How should I find the I if you have GeoGebra in front of you and you have all the tools?
Draw the biangle.
Angle bisectors. Yes. For example, which ones? A pair. It doesn't matter because the third one also passes through this. We don't need to be worried about the third one. Yes. So what I do here, I go, for example, let us see what can I do with angle bisector. Yes, we have angle bisector here. You see. So I choose this one and then I click on the. But in this case, be careful. The vertex should be named first, middle. So this would be the angle bisector of B. Yes? And what I do, I draw the angle bisector of A. I click on B. I have to click A in the middle. And then I have to click this one. So this one is the angle bisector of that. Yes? So now what should I do? I need to find the intersection point between these two lines. Okay? This D, let me change the label. Can I? Yes. This is supposed to be I. Okay, so I, but now drawing this is a little bit more problematic. How do you draw the circle? If you want to draw it exactly. Now I have the center. Of course, you might say that I don't know if GeoGebra is capable of that. Let me just take this center and try and make the circle bigger and bigger and bigger. But this is not a good way, you know. It's not clear if my hand is shaking or not. Is it 100% tangent or not? Yes? But let us make it precise. Okay? By the way, let me show you what's the difference of making it precise or not. When I just, this seems very good, yes? But then what happens if I start moving things around? I will lose the contact. Yes? So this is not constructed. This was just a random guess or fine-tuning with my hand. Yes? So you see, when I start changing this, it will lose the contact. It's no longer there. Okay, what I need to do, let me get rid of this circle now. Okay, now can you tell me what is the systematic way of drawing that circle now? Yes? From D to AB, yes, exactly. So you go here and choose this, you see, perpendicular line or perpendicular bisector. That's also, no, bisector is wrong, sorry, perpendicular line. There is no guarantee that this. And then I choose this point and I choose this and I have this. It is not bisector, by the way, but it is perpendicular. There is no guarantee this is bisector. And you see in the picture it is not bisector, yes? And then what should I do? I go to intersection point. I choose here and there. I find this intersection point. Then I am done. What I am doing now, I will take this circle. I concentrate from here up to this point F. And then I stop. Yes, this is this constructed circle. Now look what happens. I start moving things around. It doesn't lose the contact. Yes, because it has been constructed in that way. Is that understandable? So it is actually following me. Yes? Because if you construct something, it's different from just intuitively draw something. It's really, really important to be able to draw this. Even if you go to engineering, I don't know, for example, if you want to construct buildings and things like that, geometry is actually very essential too. Okay? So, is that understandable? Okay, now my question is, so what was the radius here? The radius was little r. The radius of the circle which passes through those 3 points is denoted by capital R. The same question again. If I give you A, B, and C, how do you calculate capital R? That is a little bit more tricky. Is the question clear? So let me just stop GeoGebra, go back to the board. Okay, so let me just pause the video. Okay, so I first draw the circle. This is the trick when you want to teach. Yeah, and then I draw the triangle inside. Oops, even that case doesn't work that good. Okay. And by the way, this center sometimes is inside, sometimes is outside. But the inscribed center is always inside. Yes? Yeah. I can give you some, you can demonstrate it yourself by GeoGebra, okay? But my question is that this is called a circumference circle, and the center is called circumcenter, okay? And then you have A, B, and C, and then question is that I give you A, I give you B, I give you C, and I ask you to find the radius of this circumference circle. So how should we do that? So my question for you was that, where is this center? The center is the point of concurrency of internal angle bisectors. Where is the center of circumference circle? You told me, how did we do that, by the way? We just draw this one, for example, perpendicular bisector, and the other one perpendicular bisector. They intersect at some point. By the way, let me ask you one question. If I draw the perpendicular bisector of the third one, do you think it also passes through here? Yes? So this is also another thing that we learn. So the perpendicular bisectors are actually concurrent. Why is that? Because the answer is clear. So if this is O, this is A, this is B, this is C, from A to O is equal to from A to O is equal to from O to B. Why? Because O lies on this angle bisector, so on this perpendicular bisector. So this size and that size are the same. And then this point is also on this perpendicular bisector. So if I connect this to this one, this is also the same. But now, because these two are equal in size, this point is equidistant from these 2 points, so it should lie on the perpendicular bisector of the third one. So this is exactly the proof that the perpendicular bisectors pass exactly through 1 point. And that point is the center of circumference circle. It's called circumcenter. Yes? So then, when I found that point, for finding this point, of course, I do not need to draw the 3 of them. 2 of them is enough because the third one automatically passes through that one. Yes? So, the point of concurrency of perpendicular bisectors is the center of circumference circle, and this point is the center of the inscribed circle. So these things I want you to know. Yes, we have a little bit of time. Let me just finish this statement. I want you to tell me, why do you think the heights, the altitudes should be concurrent? The proof, when I saw the proof for the first time, I was actually 12 years old. So I was very excited. So it was very, very elementary and nice. So let me tell you one thing. So what we have shown here, we have shown that if I give you a triangle, any triangle, and if you draw perpendicular bisectors, they pass through the same point. This we know for for perpendicular bisectors. Now my question for you is this. This is the last one in our concurrencies, yes? So why do you think if I draw the heights, they also be concurrent? You see, I give you a triangle. Let me try to make it clean. So this is A, B, C. I draw one height here. Okay? I draw the second height here. Of course, it will intersect that one. That's not a big deal. The big deal is actually why, if I draw the third one, again it passes through this point. This is a little bit harder because we don't have any loci in our hands, yes? Here we had a loci, being equidistant, we had a property, being equidistant from 2 points. In the previous case, for I, we had the locus of being the same distant from sides, but for heights we do not have the notion of locus anymore. But I want to show that the third one passes exactly through this point. Okay? But then let me just give you the proof and then try to enjoy the proof. The proof is very nice and very elementary, but you need to be very creative. So let me clean this one. Just concentrate on one of these heights. For example, this one. And I am telling you, take this point, from this point draw a line parallel to BC. Yes? Just draw a line parallel to BC. Yes? And from this point, draw a line parallel to AC. Yes? The logic seems a little bit convoluted. This is the type of problems that you need to do if you want to do competition. So it's really nice proof, yes? And then from this point, I draw a line parallel to this one, and I'm making a bigger new triangle, yes? Is that understandable? So if you do not look, let me call this one, for example, A prime. Let me call this one B prime. Let me call this one C prime. So I have two triangles, one the red one, one the blue one. If I ask you, what is AH, let me call it AH, what is AH? You tell me, with respect to the blue triangle, it is a height. But can you tell me, what is this with respect to the bigger triangle? My picture is not good, that's good, because you could guess otherwise. Is the question clear? The blue line AH is the height of the blue triangle. What is this line with respect to the red triangle? And why? You want to say answer?
Is it half, or is it half difference between the height from...
No, what is the name of that? So you still don't respect the geometry language. Which one is half?
The AH to be a prime H.
No, I don't see that. A prime H is not on the picture. You mean from here to here?
No, from there to the one above.
From here to here?
Yes.
This I don't know. Might be that would be true. We can discover that. But my point is that this is a height of the blue triangle. This is a blank of the red triangle. Fill in the blank. Yes? First tell me what this angle is and why. 90, why?
Because it's parallel.
Parallel. I drew this parallel to this one, do you remember? And this line is already perpendicular to one of them. It automatically becomes perpendicular. So let me clean this one, make it easier to understand. So this is 90 degrees. Okay? But can I say that this is also a height for the one, for the bigger one? There is no guarantee, because if I continue this, you see even in this full picture, you see that this does not pass through this one. So I cannot say that this one is a height of the bigger one, but it is something for the bigger one of these famous lines. What is that? What is that? It is a perpendicular bisector. Yes? Because this one is equal to this one, even though my picture is very, very bad, you cannot see it. This one is equal to this one. Can you say why? Okay, let me ask you one thing. What is this quadrilateral and why? What is that quadrilateral? Is it a parallelogram? Yes. Why? Because this one, I drew it myself parallel, and this one is parallel. So that's parallelogram. So it means the size AB prime is equal to the size of BC. Agree? And now can you finish the problem? Because this one is also a parallelogram. Yes or no? Because this one is parallel to this one is parallel to this one. So this means that AC prime is also equal to BC. Yes or no? So then what can I conclude from these two? AB prime is equal to AC prime. So this means that this line, this blue line, is the height of my triangle. Simultaneously, it is the perpendicular bisector of this bigger one. Understandable? So I can easily tell you that another height with the same reason, another height that I draw for my triangle will play the role of the perpendicular bisector of this one, and the other one will play the role of the perpendicular bisector of this one. But I just showed that if I have perpendicular bisectors, they will be concurrent. So this was a very nice convoluted proof of proving this, yes? So by being creative, we draw this one, and then we showed that any height of my triangle is a perpendicular bisector of the mu triangle. And because we already showed that the perpendicular bisectors are concurrent, so it means the heights are also concurrent. Is that understandable? Yes or no? Okay, so now we are actually relieved. I want to continue this topic for one more session, and then we go back to vectors. Okay, so yes?
This is more interesting than vectors.
Is it? So by the way, how many of you think geometry is interesting? Really or not? Okay. Okay, good. So definitely, but I have to leave it because my main topic would be vectors and linear algebra. But the reason is that I don't know how much I can cover in this course. There is something that you immediately learn when you go to Kotaho, and that's linear algebra. If you don't understand this geometry, then you will be in trouble to understanding the solid geometry, which is a little bit in space. We want to talk about line and planes in a space, okay, if we have time. But for that, I have to teach you vector in full details because we have to use them. And then we go to matrix theory, and then I think it would be end of the year. Because my method is just talk and teach, you know. So yeah, in this course, I want you to feel relaxed and learn these things. By the way, none of them is a standard in Sweden. In principle, you should at least know a little bit about these names and famous things. I think now you know about them. That's a good thing to do. Okay, don't forget to actually solve this problem. Yes, I will start solving this problem next time. I'm trying to design some questions Because designing geometry questions is hard. I have to try to pick some questions for you, but first I have to solve it myself to see that by this knowledge you can solve it or not. Okay? Any questions? Thank you.